Good afternoon, everyone. I'm really delighted to welcome you to this afternoon's lecture, which is part of the Royal Society of Edinburgh's Curious programme of events. My name is Michael Rayner, and I'm the Professor of Higher Education and Dean of Research and Knowledge Exchange, and also head of the Graduate School at the University of the Highlands and Islands. And I'm delighted to be acting as the host of today's event on behalf of the Royal Society of Edinburgh, and to be able to introduce our speaker, who's a colleague, an international expert in his field, and an all-round good egg. Now, for any of you who are new to the RSE and indeed the Curious Events programme, let me tell you just a little bit about them. Now, the Royal Society of Edinburgh recognises, supports, and mobilises expertise from across academia, business, and public service for the benefit of Scotland and the wider world. Now, RSE fellows from academia, business, and public service are among the most distinguished in their fields. They, like the Society, engage and connect nationally and internationally to share knowledge and tackle the most pressing challenges of the modern world. As Scotland's National Academy, the RSE provides independent expert advice to government and seeks to inspire the next generation of innovative thinkers. As for the Curious programme, well, this year, Curious has been running since the 4th of September and will continue until the 17th, both in person at the RSE and online, with events offering insight from some of the world's leading experts on an array of topics, addressing the general theme under the surface. This year's programme has included talks, panel discussions, outdoor events, and also comprises group discussion events. And that's a format inspired by the coffee house discussions of the Scottish Enlightenment, where people would gather to debate issues of the day. Now, if you're joining and you'd like to know a little bit more about the Curious programme, of which today's lecture is a part, please could I ask you to visit www.rse-curious.com to have a look at the programme and to book your place at some of the upcoming events. Thank you. So let's move on now to today's main event that you're all here for. I'm really delighted to be able to introduce my colleague, Professor Andrew Rae, to deliver today's lecture, which is entitled No Silver Bullet, Decarbonising Aviation. Andrew is Professor of Engineering at the University of the Highlands and Islands, where he's responsible for the university's engineering research and was recently Chief Engineer for Ampere Limited, looking after the development, certification, and flight testing of hybrid electric aircraft in the UK. He graduated from Imperial College in 1987 and was Principal Scientist and Technical Fellow in the Aerodynamics Department at Kinetic and its predecessors RAE, DRA, and DERA, involved in low-speed wing design and wind tunnel and flight testing activities for the Ministry of Defence, Airbus, Boeing, and, excitingly, if those weren't exciting enough, Formula One teams. He moved to academia in 2010 and was one of the creators of the Sustainable Aviation Test Environment, evaluating autonomous and alternatively fueled aircraft in an operational airport environment. Now, I've had the pleasure of listening to Andrew speak on a number of occasions, and I can assure you that we're all in for a real treat today. And so, without further ado, let me hand over to Andrew to deliver this afternoon's lecture. Andrew.
Excellent, thank you very much. So, good afternoon, everyone. Thank you very much for taking the time to join this session this afternoon. I'd like to talk to you about the activities that are happening within the aviation sector to decarbonise aviation and aircraft, and the work that's going on right on our doorstep in Scotland. It's quite exciting and leading the world in some of the activities that's happening. So as Michael said, the title of the talk is No Silver Bullet, and that kind of prejudges the answer to the kind of exam question about can we decarbonise aviation, and I'd like to go through some of that and describe to you some of the physics behind what is important in aircraft design, what's been happening recently in aircraft design, looking at alternative propulsion methods, alternative drivetrains for aircraft, and then, as Michael mentioned, the Sustainable Aviation Test Environment, which has been established in Orkney, which is looking at some of the operational aspects of some of this. So I'd like to start with some basic physics, really, just to help hopefully set the background as to why some of these things are challenging. So the first of the kind of challenges that we face in aircraft design is friction. So when air moves over a surface, it is affected by friction, and the air close to that surface is slowed down. So if you run your hand over a desktop, for example, you'll feel the friction. It generates heat, it slows your hand down, and the same happens with air moving over a surface. It's to a lesser extent because air is not as dense as your hand, but it still happens. And the air close to the surface is slowed down, and the region affected by that friction is called the boundary layer. We live in a boundary layer. When the wind blows, houses, trees, fences, all these things slow the air down close to the surface of the Earth. And higher up, the air is unaffected. So we live in a boundary layer. The same thing happens when air moves over a car, moves over an aircraft, and that boundary layer is really quite important when we try to do aircraft design. So that boundary layer, the region affected by friction, starts off usually very smoothly. It's what we call a laminar boundary layer. And then things like surface roughness or turbulence can cause that boundary layer to become turbulent. So the bottom left-hand picture shows air moving from left to right. The nice smooth smoke on the left-hand side shows a smooth laminar boundary layer. And then that breaks down into chaos, into turbulence, and you get the picture on the right-hand side shows that development. So the nice smooth air that starts off for a wing, so that right-hand picture shows an airfoil with a boundary layer on it. The laminar boundary layer is very, very thin. It then transitions into turbulence, and you can see that turbulent boundary layer is much thicker than the laminar one. And that has significant implications for how we design aircraft. So a laminar boundary layer, all the particles of air are moving effectively in the same direction. So the bottom left-hand picture shows on the left-hand side of it a laminar boundary layer. All the arrows are pointing in the same direction. The right-hand side of that same picture shows a turbulent boundary layer. The particles in that boundary layer are moving up, down, left, right, backwards, forwards. It's chaos. So it generates a different distribution of energy. So the laminar boundary layer, because the particles are moving in the same direction, there is no energy transfer between the boundary layer and the outside air. When we move to a turbulent boundary layer, because there's air moving up and down, it pulls in energy from the outside edge of that boundary layer and helps it negotiate regions where that energy is required. So going around corners, for example.
So sorry to interrupt for just a second, Andrew. I apologise for this. There's something appearing in the bottom of the screen that we can see that it looks like you're sharing your screen. I'm wondering if you can go and hit the hide. Perfect. Thank you very much.
Okay, I got it now.
Yeah, that's it. Thank you.
Magic. Thanks, Michael. So the two pictures here show two different types of boundary layer. I mentioned a laminar and a turbulent boundary layer, and the significance of that structure to enable air to go around a corner. So the top picture is a sphere in liquid in this case, with the air moving, or the liquid moving from left to right. And you can see that the boundary layer detaches from the surface of the sphere at around the equator of the sphere. So the wake behind it is almost the same diameter as the sphere itself. And it's very unsteady, and it causes forces on that sphere that make it move in random directions. So we have what we call a laminar separation. A laminar boundary layer separates from the surface of the sphere, and we have a laminar separation. If we glue a wire to that sphere, which introduces turbulence, we now have a transition from a laminar boundary layer to a turbulent boundary layer, and the energy that the turbulent boundary layer can bring through from outside the boundary layer within the boundary layer means that it has the ability to go around the corner further. So I hope you can see that the wake, the lighter colored area on the bottom picture is much smaller than on the top. So in this case, a turbulent boundary layer means that we have a smaller wake, and the smaller wake means we have less drag. So the bottom sphere would be able to travel further with the same energy than the top one because it has less drag to overcome. And we have a turbulent separation on the rear of the sphere. And that's the reason why golf balls have dimples in them. So the dimples cause a laminar boundary layer to become turbulent. The turbulent wake is smaller, it has less drag, so a dimpled golf ball will travel further and more accurately than a smooth golf ball would. Unless you play golf like I do, in which case there is a random element, which is the player rather than the golf ball. So drag is that wake behind the body. On the left-hand side here on this picture, there are four different shapes, all of which have the same frontal area. So again, the air is moving from left to right. Each of those shapes, the flat plate at the top, the circle, the short teardrop and the long teardrop, all have the same height. But the drag of each of those is shown on the right-hand side. So the vertical straight line, the flat plate at right angles to the flow, is at the top. And if we streamline the object as shown on the bottom, we can get down to a 20th of the drag of the flat plate at the top. And that's why you'll see sports cars and racing cars have a teardrop shape, because the drag is so much less, and the same power can get you faster. So I want to show you a quick film from Holger Babinski, who's at Cambridge University, who shows how air moves over an airfoil in a wind tunnel. And in this experiment, the air again is moving from left to right, and we have smoke showing the streamlines of air moving over the airfoil. So the airfoil is in the center of the picture. It's pitched at a certain angle of attack. And we can see that the shape of the airfoil accelerates the air over the top. And from Bernoulli's equation, we know that higher speed air has a lower pressure than slower speed air. And so we have a pressure difference across the airfoil. And that's what gives us lift. The faster air on top has a lower pressure. The slow air on the bottom has a higher pressure, and the airfoil literally sucks an aircraft off of the ground. Or if you're a racing car, it keeps you stuck to the ground. But we can only extract so much force from an airfoil. So now we see the airfoil pitching upwards. The streamlines on top of the airfoil get closer together because the air is accelerating. But we reach a certain point where the air at the back of the airfoil starts to break down. So you can see some unsteadiness at the trailing edge of the airfoil. And then we get total flow breakdown, which is what we call the stall. So we can generate lift from an airfoil, but only up to a certain point. And when the stall happens, we lose all of the lift. So this again is a bit slower. So the airfoil is pitching upwards, start to see some unsteadiness at the back. That then moves all the way forward and we get stall. So in steady level flight, with an aircraft flying at a constant speed, at a constant altitude, the lift required is equal to the weight of the aircraft, and the thrust from the engines has to overcome the drag of the aircraft. Now, the two graphs at the bottom there show how the lift on the left-hand side varies with angle of attack, and that is a graphical representation of what you just saw in the wind tunnel. As you pitch the aerofoil up, so the angle of attack is at the bottom, as we increase the angle, the lift goes up until a certain point when we get a stall. On the right-hand side, you can see the drag. As the aerofoil pitches up, the drag goes up, and when we get a stalling angle, the drag goes up exponentially. So to design an aircraft, we need to get the maximum ratio of lift to drag. The best cruise performance comes from the ratio of lift to drag. So if we combine those lift and drag curves, we get the lift to drag versus angle of attack curve. I hope you can see that the peak of that curve is around 2 to 4 degrees. So that's where we design aircraft to fly, because they are at their most efficient. Unfortunately, though, if we add weight, we need more lift, and more lift causes more drag, which means we need more thrust, which means we need more fuel. And if we have to increase the size of the aircraft, that increases the surface area of the aircraft, which, because of the friction, generates more drag, and that means we need more thrust. And we run the risk of getting what's called a weight spiral. So if we add payload, for example, more passengers, we need more lift, a bigger wing, we need more thrust, which means bigger engines. A bigger wing and a bigger engine means more weight, which means we now need to generate more lift, which means another bigger wing. So it's a compound problem, and we have to avoid this spiral of increasing the weight to increase the performance. So that was some of the physics behind aircraft design. Now coming into some of the practical aspects of that. So there is some good news. Over the last 50 years or so, the efficiency of aircraft has improved significantly. So if we start in 1975 with the Airbus A300, the first of the Airbus aircraft, that had a lift-to-drag ratio of around 14.5. The current generation of aircraft, so A380 on the right-hand side there, had a lift-to-drag ratio of 20. That means that for every newton of drag, we had a 20 newtons of lift. And things like the 787 and the Airbus A350, sorry, are now up at 21, 22 lift-to-drag ratio. So the efficiency has increased considerably since the first generation of modern jet aircraft. And that's helped the fuel burn on aircraft come down. So the bottom axis here shows the evolution of aircraft through the decades, starting with the Comet 4 and the Boeing 707, which were the first jet passenger aircraft. And you can see if we take the Comet 4 as 100%, the A320neo, which was introduced into service just under a decade ago, is burns a fifth less fuel. Oh, sorry, 4/5 less fuel than the Comet 4. So we're down at 20% fuel burn compared with aircraft of the 1960s, and that's a massive decrease in fuel burn. Traditionally, the main reason for doing that has been to increase profit for airlines, and now we have a different imperative. We know that burning kerosene is bad for the environment, so we have to come at this from a different angle. And the bad news is that despite COVID, so this is a graph showing how air travel decreased during COVID. So 2020, during the lockdowns, air travel reduced significantly. And you've probably all seen pictures of aircraft parked up at airports and the reduction in aircraft usage. Although in our part of the world, in Scotland, things like the public service obligation route still operated in the islands because they are quite literally lifeline services. And people were interested to see how aviation would recover from that COVID dip. And if you ever go through an airport recently, you'll see that pretty much nothing has changed since pre-COVID. Air travel is predicted to grow still, and even at low forecast levels, the increase in passenger traffic by 2050 is more than double what it was pre-pandemic. And so taking the US, these reasonably old figures, but it gives an indication of just how much aviation contributes to the burning of carbon-based fuels. So these are 2017 figures from the US, and you can see there that jet fuel accounts for 12% of the total burn. And also there is aviation gasoline. So some of the aircraft that fly still run on effectively leaded petrol, including the British Norman Islanders that fly around the islands in the north of Scotland. So it's not the biggest contributor, but it is a significant contributor, and especially when you add things like the particulates that get emitted at high altitude and the formation of contrails and clouds, it's worth considering. So we have to do something, and that requires alternative propulsion. So in Scotland, that's partly been driven by the Scottish Government's Green Deal. It was understood that aviation needs to change, and doing nothing is not an option. So as part of the Scottish Government's Green Deal, there's an ambition to put the Highlands and Islands on a path to becoming the world's first net zero aviation region by 2040. And that requires the Highlands and Islands airports, who operate most of the airports in the north of Scotland and are the air traffic navigation service provider as well, to be part of that path to zero emissions, and more of that later. So now some of the analysis of some of the alternatives that are being proposed. Part of, you've probably heard of hydrogen propulsion as being one of the significant alternatives to kerosene. So in the orangey column to the right-hand side here, we have kerosene, which is the fuel, jet fuel, which is used by most airliners. And it has a gravimetric efficiency, which means the available energy per unit mass of 98. On the left-hand side of that, we have hydrogen, both liquid and gaseous hydrogen. And you can see that the gravimetric efficiency is much less than kerosene. So already, even just looking at this very simple metric, there are challenges around getting enough energy out of the same mass of fuel compared with kerosene. Ammonia is an attractive alternative if we use this metric, but ammonia is a very tricky substance to handle. And then there is cost. So the Aerospace Technology Institute in the UK did a program called Fly Zero, and it ended 18 months or so ago, looking at alternative propulsion and including hydrogen. So we currently don't really know how much green hydrogen is going to cost. We know it's probably going to be more than kerosene costs today. So there has to be an incentive for people to use hydrogen, and that might be a kerosene with a tax on it, or replacing kerosene with sustainable aviation fuel, SAF. And this is another graph reinforcing the challenges with different propulsions. So at the top middle almost, there is kerosene. So it has a very good volumetric energy density. So the amount of energy you get from a volume of the fuel is high, and so is the same energy from a mass. Liquid and gaseous hydrogen win on the mass because they are lighter, but the volume required to get that same energy is massive. And then batteries are at the bottom left-hand corner. You get a small amount of energy from a very heavy mass, and I'll come to that in a minute. So hydrogen can be used in a couple of ways. One is to be burnt directly within what looks effectively like a current jet engine. So we can use hydrogen, gaseous hydrogen and air to burn in a combustion chamber in a conventional jet engine. But we still get the conventional byproducts. We still get particulates that form the contrails, and we still get water. We can, however, replace those with fuel cells. So we use hydrogen to run a hydrogen fuel cell, which effectively creates electricity to drive an electric motor to give us the same thrust. And that has advantages because it doesn't generate the particulates that gas turbines do, but the technology is in its infancy. And again, this is a picture from the ATI's Fly Zero program, and it took two different sizes of aircraft. So on the left we have the ATR 72, which you're familiar with Logan Air services in Scotland. They fly a lot of those, and then the size of aircraft that if you go on holiday to the continent, you'll be familiar with an A320 or a 737. And on the right-hand side of each of those is the current volume of fuel required for a standard flight. Compare those with the same graphic going left from there in terms of ammonia, gaseous hydrogen, and liquid hydrogen. And you can see that the volume required to get the same energy, to give you the same range, is considerably more, especially with gaseous hydrogen. It's massive compared with kerosene. And there are also problems with hydrogen itself. As many of you know, the hydrogen is the simplest possible molecule. It's very tiny. It will leak through anything. It's very abundant, but not in gaseous form. So we have to generate that, and that requires energy, and that energy has to come from a sustainable way. Experience from the oil and gas industry shows that hydrogen can embrittle things like steel. So it's a tricky thing to try and contain and to manage. And there are historical precedents around why hydrogen can be tricky to handle. So moving to electric, in the US, NASA has invoked the X-plane program on the X-57, the Maxwell program, to look at what's called distributed electric propulsion, looking at lots of small electric motors to replace two larger conventional aircraft. That program is now finished, I believe, without flights, but the lessons learned have been illuminating in terms of the capability of batteries and electric propulsion. So they too are not without their problems. If you ever looked in a big, either a hybrid electric car or other type of lithium-ion battery, it's a series of cells that are made up of interconnects, and managing the heat generated by those batteries, especially when charging and discharging, is a problem. And the materials we use to make those batteries too is troublesome. Things like the cobalt and lithium that are used are found in very few places. So the resilience to global markets of these things is difficult, and the World Bank predicts that with global demand for lithium-ion batteries will grow by a massive amount in the next few decades, and aviation has to compete with that. Having said that, there have been some very good examples of how we can use batteries for aircraft, and Rolls-Royce created the airspeed record for a pure electric battery-driven aircraft using the Axel program, which flew 2 years ago now, and achieved a speed record of over 330 miles an hour, based purely on batteries and electric motors. But this graph shows the challenge for a conventional aircraft. So the red dotted line there shows that for a conventional aircraft, 40 to 45% of the aircraft is, when it takes off, is fuel. a bit less than that for kerosene. And the range on the bottom axis there is the real key for understanding how these things challenge aircraft design. So for pure battery, because they are so heavy, you can either reduce the payload, reduce the number of passengers, or you don't fly as far. So for a kerosene aircraft that can fly over 3,000 nautical miles, a battery aircraft would be able to fly less than 500. So there might be advantages with hydrogen, but then we get a problem with volume, which I'll come on to shortly. So again, as part of the Fly Zero program at ATI, they identified the likely power sources for the aircraft that we use today. So essentially the horizontal axis is range. So wide body is transatlantic down to sub-regional, which is the aircraft that fly between the islands, for example, in Orkney. So those short range aircraft could be satisfied by battery electric, but the long range currently will only be able to remove carbon from their usage by using sustainable aviation fuel. That's using alternatives to kerosene that come from a green and sustainable source. And hydrogen might be able to do that in the future, but there's still lots of questions to be answered. So the ATI suggested 3 types of aircraft. So the regional at the top, it would be replacing the ATR aircraft that Logan Air currently use on most of their northerly routes, down to a mid-size, which is transatlantic size aircraft. But one of the things you might be able to see here is the increase in the volume of the aircraft. And here's the reason why. So this is an aircraft, the green lumps there are the hydrogen fuel tanks. And you can see that almost a third of the fuselage is taken up with fuel tanks. So assuming even that you can make that safe with hydrogen leakage, you've lost a third of your payload. So the amount of people who pay for a seat has gone down by a third. So the economics become challenging. So for the same number of people, the aircraft has increased in size. And going back to the physics that we talked about earlier, that's a bigger aircraft, more surface area, more friction, more drag, and you need more thrust. So we start getting into some challenging economics. But we've been trying to understand how those economics work. And one of the projects that Michael mentioned I was involved in as chief engineer in the UK for Ampere, which took a modified Cessna 337, which has an engine at the front and the back. So we have twin engine reliability, but with a single thrust line. And the front engine was replaced by an electric powertrain. So in that front compartment, the standard internal combustion engine has been replaced by the electric motor, which is the black donut behind the spinner. And then we have an inverter. So the motor runs on AC current, the battery delivers DC current, and the battery pack is underneath the aircraft in the pannier, the white pannier that you can see underneath between the undercarriage there. So not only have we replaced a lot of that internal combustion in terms of volume, but also reduced the weight considerably. So we need to consider weight and balance for the aircraft as well. That aircraft first flew in the US. It recorded 100% dispatch reliability. So the aircraft flew very, very reliably and recorded 24 flights over 28 days, the longest being 341 nautical miles. It was then taken to Hawaii to run on some indicative airline routes within the islands in the Hawaiian archipelago. So again, it did 22 flights over 17 days and it was 100% reliable. I show this video because the Cessna 337 rear undercarriage is probably the most ungainly retraction mechanism I've ever seen on an aircraft. The rear wheels waggle around a bit until the actuators catch up and then drive them back into the fuselage. So that aircraft then was brought to the UK, to Kirkwall, and Wick, and we flew between those two places a number of times during the summer of 2021. Again, 100% reliable. The right-hand side is a picture of Kirkwall Airport taken from Amper's Cessna during the summer of 2021. It was then ferried. It flew from Wick down to Exeter and did similar tests between Exeter, Newquay, and Land's End. So many of you may know that the Wick Airport is John O'Groats Airport, so it flew from John O'Groats to Land's End, and the aircraft is now in Alaska doing some flights up there. So one of the things that has become a challenge for these aircraft is operational aspects of it. So we have things like charging. So if you own an electric car, you'll know that not every adapter or charging point can work on your car. They are specific to certain cars. And we need to understand how those aircraft can be designed so they are safe, because it's a whole new technology that we need to develop safety standards for. So there's a whole load of operational and infrastructure and energy questions that we need to answer. But the good news is it changes at first. So the left-hand picture there is what a mobile phone looked like when I was a kid. The battery pack has reduced significantly, so we can carry them around in our pocket now. And hydrogen has had a bad press in aviation ever since the Hindenburg, although that was caused by the skin of the aircraft rather than the hydrogen itself. So we've moved on, but not without risk. So there are recent accidents from which we will learn. So on the left is Zero Avia's aircraft at Cranfield. On the right is Vertical's eVTOL aircraft at Kemble. But aviation has proven itself very good at learning from mistakes. That's why we do testing, and neither of these accidents resulted in any injury. And if you're interested in how aviation has learnt from mistakes, I recommend a book called Black Box Thinking by Matthew Syed, which compares aviation with other sectors about how well they learn from mistakes. So finally, talking about the Sustainable Aviation Test Environment, it was set up under the UKRI's Future Flight Challenge Programme to investigate alternative propulsion and alternative operations of aircraft on realistic use cases in an operational environment. So Kirkwall is an operational airport. It has timetabled aircraft both to the mainland and between the islands. It has oil and gas helicopters, general aviation, and everything you'll see at a busy airport, but in a less dense air traffic environment. So looking at the energy infrastructure, the aircraft themselves, the digital infrastructure, so the communications between the aircraft and the ground, and involved the local authorities as well. So as part of that, a new hangar was created. It's got electric charging points. It will have a hydrogen electrolyzer to supply hydrogen aircraft. So it is a base for the evaluation of these new types of aircraft based at Kirkwall Airport. And we've had some significant successes. On the left-hand side is Amper's aircraft flying, as I mentioned, 2 years ago, and Windracer's excellent drone that delivers a 100-kilogram payload over a 1,000-kilometer range worked for the Royal Mail to deliver parcels to some of the outer islands in Orkney. And on the right-hand side is the first phase of the project, the flights that we flew from the mainland to Orkney and then up to Shetland and to Fair Isle. And the left-hand side illustrates what we had planned for the current phase of the project, which has expanded to include the Western Isles and more routes between the islands, and possibly a route to Bergen in Norway. So finally, just a video of that project.
SATE is the UK's first low-carbon aviation test centre to be located at a commercial airport. It's based at Highlands and Islands Airports Limited's Kirkwall Airport in the Orkney Islands. A range of exciting technologies are being explored, including low-carbon aircraft such as hybrid electric and hydrogen, as well as the use of synthetic aviation fuels. Unmanned aerial vehicles, UAVs, are also being trialled, demonstrating real-life service demands to connect communities. As an early adopter of other low-carbon technologies, Orkney is an ideal living laboratory for testing aviation technology, offering a real-world environment with harsh weather and inter-island routes.
Orkney was the ideal place to set up this environment. There's a few reasons for that, not least of which is the buy-in from a local community. People in Orkney are really excited around renewables and sustainability. Hopefully, one of the benefits of this long-term will be that we manage to improve connectivity as well.
Technologies range in scale, from the smallest drones to commercial passenger planes. Airport infrastructure supporting the development of sustainable aviation testing has also been put in place. A large, purpose-built hangar fitted with charging points gives ample space for multiple aircraft and technology teams. At over 30 metres long, it can easily accommodate wingspans of up to 20 metres. Dedicated on-site offices are well equipped with super-fast broadband, offering a meeting and work space for technology developers.
Windracer's Ultra UAS is a twin-engine aircraft, uncrewed aircraft, that is capable of carrying 100 kilograms payload at a distance of 1,000 kilometers. It's been specially designed for transporting aid and for logistical transport in rough conditions, in unprepared runways, any environment really. It is very important for us to be able to have this test environment. We have a hangar here where we can store and do maintenance to our aircraft. We have some offices here where we can have our ground control station, where we can have all our communications equipment, so we can get our staff ready and basically test it once we have the opportunities and the weather windows to do it. For us, it is vital to have this kind of facilities where we can come test in a safe environment, in a controlled environment.
SATE provides the blueprint for net zero regional aviation, placing the UK at the forefront of the transition to low carbon flight.
For HIAL, its Sustainable Aviation Test Environment is the first step to a wider goal of decarbonising aviation in the north of Scotland and the islands.
SATE, providing a test centre to accelerate the industry towards net zero, where blue skies become a little bit greener.
So I've just given you an indication of some of the challenges that we face. They are significant, but we have to start somewhere. When I talk to school pupils, I say that I hope if they choose aviation as a career and get to the same point in their career that I'm at now, they will look back and laugh at what we're doing, because they'll have come up with a much better way of doing this stuff. But we have to start somewhere, and that's what we're doing. So thank you very much for your attention.
That was a fascinating talk. I've learned an awful lot, and there are already some questions in the Q&A section. So I'm just going to kind of run through them from top to bottom so far. And I've got something I'd like to ask myself. And I apologise for colleagues if I get pronunciation of things wrong. But here we go. The first one is, I think it's from Moni. And this is, I think, when you were dealing with the sort of design aspect of your talks a bit earlier on in the presentation. And the question is, would peppercorns of craft design aid lift? And they're using the crashing a meteorite as an example?
I'm not sure I understand the question. By
I
peppercorns,
think
do you mean surface roughness?
Yeah, I think that might be it. It was when I think you were talking about the golf balls and the dimples and so on and so forth.
Roughness in the right place can aid aircraft design, and they're a kind of analogous technology is what's called riblets. So shark skin has very small troughs in it, and they have been applied at the right scale to aircraft skin. It has shown a benefit, but the manufacturing requirement and the maintenance requirement to keep them clean means that any benefit you get is outweighed by the cost and the weight. So everything in aircraft design comes back down to weight. Yes, there are some really good things we could put on, but the benefit is outweighed by, quite literally outweighed by, other things.
Very good. From the same colleague, a question about using heat to store electrical energy. Would that help, presumably, to prolong the life of batteries and mean that you could get even further distance out of the same battery?
Heat is one of the real problems with especially lithium-ion batteries. So especially when you charge or discharge them quickly, the thermal management is the key to how fast you can do those things. So removing heat is the key. Adding heat is probably a bad thing. So if you've ever seen a lithium-ion battery in thermal runaway, you don't want to go anywhere near it, especially if it's on an airplane. So I don't think adding heat will help. Most of the time, we're trying to remove heat from a battery system because that causes problems.
Again, thank you very much for that. And got another question from Finlay, and this is, hi Andrew. Does it frustrate you that a lot of venture capital funding and therefore aerospace engineering talent has been directed towards eVTOL, I guess, rather than ectol in recent years? And says our group, which is Safe Landing, believes it's quite a big waste of time, money and talent on a mode of travel that's inherently inefficient and will burn through the batteries. I was wondering on your thoughts on that.
Well, I think the whole question of urban air mobility, which is where eVTOLs are aimed, there are some significant operational questions that haven't been answered. So, for example, a helicopter, if the engine fails, it will auto-rotate to a certain degree. So the pilot has at least a little bit of choice over where he puts the aircraft down. eVTOLs, by and large, don't auto-rotate, so they just drop. So to do that over a city would be a bad idea. Yes, I think some of the things that will come from them will be useful, but I think that the thing that worries me most is that some of these companies are keen to get things flying because that's what attracts investors. Hardware attracts investors, whereas the traditional, more considered design approach is less attractive, but is required to do these things. So I worry that some of these companies haven't done the due diligence in their development in the race to get something physical to test. That's a very cynical view, and some people have done it very well, others have done it less well.
Thanks very much. That's great. And again, just moving on, question from Jack, and just wondering what your thoughts are on the potential of airships for short haul flights in the future.
Interesting question. Hybrid air vehicles have been part of our project, looking at the use cases and routes for their airlander aircraft, so the heavy lift aircraft. There is certainly a market for that. It will be limited by weather, especially in the north, but the transport of non-perishable goods in an environmentally friendly way is attractive, and especially if it can land anywhere. So it can land on water, it can land on non-airfield sites. So it opens up a route network that currently isn't possible. So yeah, there's certainly a market for it, but there are again some operational challenges. But if you've not looked at Airlander's site, HAV's site, then go and have a look at it. They've done some really good stuff.
Good stuff. Thank you very much. Couple of questions here about hydrogen. The first one is, what would transform the use of hydrogen as a fuel for mid and long distance aircraft? And then the second one, is there a difference between hydrogen fuels and SAFs?
I'll take that last question first because that's the easiest. So SAF is essentially interchangeable with current kerosene. So it's effectively kerosene grown from non-carbon sources. So you could fly current aircraft on SAF, and current aircraft have been flown on SAF without major modifications. There was a concern around the effect they have on things like rubber seals in the engines. So I think at the moment you can run a 50-50 blend of kerosene and SAF without any problem. That will change to 100% in the near term. Hydrogen is a lot more tricky. That requires a whole new different fuel system. It requires a whole new different propulsion system, and the fact that it will leak is a problem. Whether that's vented to atmosphere, hydrogen in the atmosphere is not a great thing either, depending on how it reacts. But managing that mixture of hydrogen in air so that it doesn't become combustible is the real thing.
Okay, thanks very much. A couple more questions coming in. One is actually just a note of interest. Apparently, Harbour Air in Vancouver is electrifying its DH Beaver seaplane, and there's a link to that.
Yep.
So that would be for colleagues to pick up and have a look at that. Just for noting. Next from Brian here. This is a great presentation. Thanks. When is SATE2 likely to start, please? The Outer Hebrides Climate Hub and Community Planning Partnership Climate Change Group would like to participate in discussions. So have you got any idea when that might be taken?
So SATE2 has already started, and any conversation with people from the Western Isles would be really good. So if we can make contact afterwards, that would be good. But we're now looking to a SATE3 and what that might look like. So there are various hub and spoke activities. So you saw the wind racers aircraft there. So one of the things is delivering large quantities of freight to Kirkwall by conventional means, delivering that large amount out to the islands by wind racers drone, and then using a smaller drone to take that to individuals or businesses. That will work equally well in the Western Isles. In fact, there are some additional interesting use cases in the Western Isles, so especially with NHS and other activities. So yeah, happy to have a conversation. Please get in contact.
Good stuff. Thanks very much. And another one here. You talked about batteries in that. So the question here is, do solid state batteries offer a step forward for electric powered aircraft?
They do, if you believe the PR. It will take a long time for these new battery chemistries, whatever they are, whether it's solid state or sulfur or whatever, to be proved safe enough to go on an aircraft. So there is a development cycle that needs to happen with those. I think solid state is probably the best avenue for adoption into aerospace, just because of the weight saving.
Here's a potential investor question, I think. So There you go. You better do a disclaimer up front on this one. But the question is, which companies in the electric oblique hydrogen aircraft space do you think are more likely to succeed and have the most orders in 2030?
Yes, the cost of shares goes up or down depending on the market. Whatever other disclaimer I have to put on, I think in the UK, Zero Avia have done some fantastic stuff in developing their powertrains. The other company I would recommend looking at is Cranfield Aerospace Solutions, who are running Project Fresson, which is a hydrogen-fueled Britten-Norman Islander that hopefully will fly in the north on the PSO routes in the not too distant future. So I would shy away from recommending which one would win, but those two companies are doing stuff in the UK, so they are visible to us and worth looking at.
Thanks very much. And I'm going to wrap up in just a wee second now. I know time's going on, but I was curious myself as you were going through the presentation and thinking about other developments that have taken place, and just wondering how much collaboration is actually going on worldwide to standardize some of these technologies, because there's always a racing competition, and then that means you've got differences, and that can even in the way you maybe recharge the batteries that we now.
Yeah.
So is there a lot of collaboration in this, given the stakes are so high for carbon emissions?
There is recognition that things like the diversity of charging options for electric vehicles will not work for aircraft. If you land at an airport and your plug doesn't fit into the plug that's at the airport, you've got a problem. So there has to be standardization, and people like SAE in the US and BSI in the UK are looking at those standardizations. That has to happen in the same way that it does with existing fuel systems. So if you've got a kerosene fueled aircraft and you land at an airport, you will be able to refuel.
Yeah, thank you very much indeed. Andrew, that was an absolutely fascinating talk, and lots of people are saying thank you very much for that. You'll be relieved it's now over and you can breathe a sigh of relief again, but we're extremely grateful to you for what has been a tremendous and fascinating